All right, lesson 6.5 on logistic equations. This is a BC topic again. Exponential growth modeled by this, c times e to the kt, or PERT, assumes unlimited growth. It just grows to infinity, and that's unrealistic for most population growth. There's a capacity, a maximum. It's going to grow up to a certain amount and then level off. That's what a logistic equation does. It increases to a certain amount and then it levels off. And so this is what that looks like as a diffq. And so in this situation, m is the maximum amount or the carrying of capacity, and k is the rate that it's growing at. All right, so the solution to this equation is in this form, where the numerator tells you the maximum population or whatever it is. That's the highest amount it could be. It also gives you a asymptote, a horizontal asymptote at that number, where it's going to go up to that and then that's it. And then you can see the denominator and the rate and the maximum capacity, and t is a variable, c is a constant, and so on. C is not the initial amount to begin with. All right. So if I want to write a differential equation based on this information, a national park is capable of supporting no more than 100 grizzly bears. That's what m is. And so when I look at this dp by dt, then m is that number, k is that number. So it's 0.001 p, and then m, the maximum amount, 100 minus p. That's a logistic equation, plugging in the values that you're given. The slope field for this is shown to the right here. And then where does there appear to be a horizontal tangent or asymptote? And I said at 100 right here, you can see that it appears to be like that's it. It comes together there at 100. So when it's equal to 100, you can see that there's a horizontal asymptote. What happens if the starting point is above this asymptote? So if you start above, it decreases to 100. What happens when you start below? It increases to 100. Then it says, if the park begins with 10 bears, sketch a graph of this on the slope field. So I'm going to start with 10, and then I'm just going to follow the flow of what's happening here. And then when I get here, it reaches that kind of maximum amount. And there's that logistic growth where it's increasing, and then it's going to level off. And then it says, can you solve this differential equation? I need you to have patience as we solve this. So we start with dp by dt is equal to 0.001 p times 100 subtract p. That was from the first page. And we're going to solve it like we normally solve a diffq. So we're going to separate the variables. We're going to integrate and solve for p to the best of our ability. We're going to do it together. So first of all, to separate, I'm going to multiply by dt. And then after I multiply by dt, I'm going to divide. So I'm going to divide by this to both sides. And on the other side, I have 0.001 dt, just to separate the variables. When I integrate this, on the right side, it's pretty simple, 0.001 t. But on the left side, I'm going to have to do this by separating it into two fractions. So on the side, I have a is going to be the first. It's already factored out. And that's going to be equal to 1 over this. So I'm going to separate it into two fractions. So the if I multiply to make common denominators, A is going with 100 minus P, and B is just P, and that's equal to 1. And that's what I'm going to use. So now I use the zeros. So when P is 100, that gives me 100B is equal to 1, divide, and that gives me 1 over 100. The other one is 0. So when P is equal to 0, it leaves me with 100A equaling 1, and when I divide, I get 1 over 100. So I got both of those for B and for A. All right, come back here. So now I can separate it into two. So for the first one, A, right here, I'm going to write 1 over 100, and that's 1 over P. The second one, for 100 minus P, that's B, that's also 1 over 100. Oop, there it is. And then if I integrate the right side, I get 0.001 T plus C. So I just have a variable connected to it. These are going to be logarithms. So this is going to be 1 over 100, the logarithm. Just use the denominator. For this one, the hook, the derivative of the bottom is -1, so this needs to be negative. So it's going to be negative 1 over 100 ln 100 minus P. And I did step number 2. So I integrated this. Our next step is to solve for P. So what are things that I can do to make this simpler so I can get P by itself? So I'm going to multiply everything times 100. Now 0.001 times 100 moves the decimal 2 to the right, so that's 0.1. And then I'm just going to change that constant. So 100 times C is just a new constant. Now I'm going to use properties of logarithms. So when you're subtracting, it means you're dividing. So I have P divided by that is equal to... Oh, what happened? There's a T there that I forgot. So multiply it to 0.1 T plus the constant. Now to solve this logarithmic one, we're going to write it exponentially. We still have these absolute value bars in here, but we know we can remove the bars and then just rename the constant. We'll call that 3. We're getting there. I want to get P by itself here. So I have P over 100. P divided by negative. So I got P. Oh, wait a second. What should I do? Well, let's flip it around. So I'm going to put 100 minus P on top and just P on the bottom. And then this just flips it like this. Now I'm going to separate this. So it's 100 over P. Now P divided by P is -1, but I'm going to add it to the other side. And honestly, if I wrote this, I can write this with a negative exponent. That'd be easier. So if I add it to the other side, I have C e to the negative 0.1 t plus 1. So I can not have a fraction there. There's no fraction there. CE negative 0.1 t. So it's not a fraction. Because at this step, we are going to do the reciprocal again. And then the last step is to multiply by 100. And then I have my answer. So I solved that diffie-q and solved for p. Not a simple task, right? And then after that, solve it with the initial condition. So I'm going to keep, where do I have room? I'm going to move up here. So the initial condition is at, the initial population is 10. So when t is 0, the answer is 10. I'm going to do that above here. So I'm going to plug in 0 for t. So this gives me e to the 0, which is 1. So what must C3 equal for this to equal 10? So it must be 9, because 1 plus 9 is 10, and 100 divided by 10 is 10. So the constant must be 9. So if I go back and write down what this is again, this is what it looks like. 100, 1 plus 9 e to the negative 0.1 t. And you did it. That's where we got to, using the initial condition. That's called a logistic equation. That's the calculus view of it. That's good work. Look at all that good work right there. All right. Part E says, instead of solving the differential equation, use the general form to find the same solution. So the general form here, m we said was 100. C we don't know yet. But it's E, we said the K was 0.001. That was at the beginning of the question, 0.001. M, again, is 100. And then T. And then find the same solution. So we started with, there was 10 bears to begin with. And we solved for C doing this. Negative 0.001 times 100. Move the decimal 2 to the right. And then if I plug in 0 for t and solve it, we get the same answer. C is equal to 9, and you get the same answers we just had. Easier, yes? And there it is. So negative k and m, they multiply together, come up with 1, negative 0.1 t. Find the limit as this approaches infinity. So what's the right end behavior? Where is it getting closer and closer to? And so the numerator is going to be the end behavior. So this population is getting closer and closer and closer to 100 the further we go in time. And that's the greatest value it's going to get up to. So that's what this is. What's the right end behavior? So in that case, it's the numerator gives you that. That's the horizontal tangent. When will the bear population reach 50? So we take what we have and make it equal to 50, and we're going to use our calculator and solve this. So let's see, make it equal to 50 and solve it. Let's take our calculator out. We'll do it together. So we're going to go menu. Here, clear this up first. All right. So let's go menu, algebra, solve. And we want to know when it's 50. And it's a fraction, 100 over, remember go control divide for a fraction, 100 over 1 plus 9. It's E, not the bottom E, not the letter E, the number E. That's on the left. And then it's negative 0.1 t. Make sure I typed it in right. And then go comma t, move the cursor, go comma t, and then solve it. 21.972. So in almost 22 years, the bear population will reach 50. Pretty slow, right, for that? And then it says, when is the bear population growing the fastest? to know when it's growing the fastest, growing means the derivative. So that's the diffie that we started with. So that's 0.001 p, 100 subtract p. That's the diffie. When is this growing the fastest? We have to take the derivative of that equal to 0 and solve it. So we have to take the derivative of this derivative to know when it's growing the fastest. So growing means it's the derivative. Fastest means I got to take the derivative again of this derivative. So let's put this into the calculator. So again, menu, algebra, solve. And then we're going to do derivative. So menu, calculus, derivative. And then we're going to type it in. This is going to be in terms of p. So use p on the bottom of your keyboard. And then we're going to type in 0.001 p. Now, I have to go times and then parentheses. So it won't understand it if I just go 0.001 p parentheses. I need times and then parentheses. And then it's 100 subtract p. Close it. It's already closed. Make it equal to 0. So to know when it's a maximum value, when it's growing the fastest, we take the derivative of that derivative equal to 0 and then comma p. And look at that. So the answer is 50. So if the answer is 50, the question is when. So at 50, that would be the same answer. So it's growing the fastest when the population is 50, and the population is 50 when? At almost 22 years. That's when it's growing the fastest. So if you looked at the graph before, that's when it's the steepest. All right, Mr. G Math over and out. Till next time.